symmetry. So what? Filter filter those. So then, when we have a group, then we're going to use applied symmetry. We will find, but after that, we still may have several. So in this case, the number step, step 4, we are going to apply the Holmes law to determine the ground state. So among those, which one corresponds to ground state spectroscopic notation? So apply, then apply. Okay, so I didn't introduce this Holmes law, but now I'm going to do that since then we are going to do some application. So this one, for S, how to determine the capital S? Because here, right, this one, S. S, the lowest energy level for the S is largest. Take the largest. S value, which corresponds. For L, same thing, okay, largest. So that means if we still have a group after the fill out this symmetry, still have a set of this spectral notation, spectroscopic notation, we're going to select among them which one S is bigger, which one L is bigger, and then for J, so for J here is equal to L minus S for less half. Less half share. Or equal. Less half equal. Plus S. Okay, so how to do that? Let's to play with the examples. Then we are going to see how to apply this strategy. So example here. Examples. Here the textbook only make the statement, didn't have the details, formulas, and the steps, so I'm going to here summarize here. I hope to give you clear the way or method to determine. First one. What this means, closure means we have the total electron number of electron occupied all the shell, no any open shell, right? So first one, helium. Now, helium atom, first we are going to see how much the number of the atoms, the electron Z equal to, right? So first, Z equal to, okay, that's step one. So step one, Z equal to 2. So then we start from the energy left order, right? So now first order is 1s. 1s. How many we can occupy? 2, right? Spin up and down. So according to the Pauli crucible is here. So that is the configuration, electron configuration. That means we have 2 electrons, and these 2 electrons to go to the ground state, we go to the lowest energy as possible. And the lowest here is the n equal to 1, L is S, right? L equal to 0 is S orbital. So for this subshell, we have, let's see, maybe subshell. We have only allowed 2, right? Is S plus F1, so that is conclusion. So we finished step 1. Then we go to step 2. Step 2 here, total L. This case, there are 2 ways. This case, let's just first do this. So L1 plus L2, right? And L1, okay, here, let me just also write down. N1 equal to N2 equal to 1, right? L1 equal to L2 equal to 0 because that's S orbital. So here, 2 S orbital are 0 plus 0, right? So that would be total is 0. And S is S1 plus S2. And we already know that we either up and down, so that we also give a 0, right? Or you can use this. So L, this is addition to orbital angular momentum. So L be smaller or equal to L1 plus L2, larger or equal to L1 minus L2, right? This one is 0. This one also 0. So L equal to 0. Because this case is simple since only 2, so we apply the additional 2 orbital angular momentum, then we can immediately determine the quantum number L, right? And S also same thing. So additional 2 spin, which is this one is a half minus half is equal to 0. This one half. Oh, sorry. Yeah. Actually, from here, we already know that's be 0 because cancel together. So here, if I do this one, then you have used this symmetry here. So now, if I use this one, so then that gives us S. I just extend more to some different way, right? S is 0 and 1, right? The 2 values. Now then here, now with this, I have this J equal to. G is L plus S larger or L minus S, right? So here, if I use this way, that is immediately get L equal to 0, S equal to 0. But if I use this way, so I have L equal to 0, but S has 2 orbital. So now I'm going to use this one. Here, for S equal to 0, when S equal to 0, because L is always 0, right? So then 0, 0, 0, so that G is only 0. But for S equal to 1, L only have 0, right? So here, this is 1, and this is 1 again. Wait a moment. 0, this is 1, and this is also 1. So G equal to 1. So from, okay, if this case, or this case, the spectrum of this one, 2S plus 1, right? 2S plus 1 L, G is equal to S equal to 0, so that's 1. L is 0 is S, and G is 0, so this one. But if this one, S is 1, 3, sorry, this case, 2S plus 1, L, G is, S is 1, so 3, L is still 0, G is 1, right? I think this one is not really easy. This one is okay, maybe let me see this case. It spends too much time. Since I jumped this one. If this one is very easily, right? So this is just L is S and the S 0, so the 1, 0, so that is very easily to obtain. This one, let me see if we go to here. We go to here, so the symmetry here, and you know the symmetry should be anti-symmetric. Then we have a radial part. And the radial part, you will see here, this N or same. So radial part should be symmetric, right? We already discussed. And then for the angular part here, so we also symmetric since this L has a 0. Since 2L are same, so that's it. Then there's the spin part should be anti-symmetric. So if this one anti-symmetric, you remember we have spin for this case. So spin we have several states: 0, 0, 0, 1, 1, 1, 0, 1 minus 1, right? Remember we have 4 states addition. So this one is symmetric. Sorry, is anti-symmetric. And these 3 are symmetric. So S, M, S, we will have addition, we have a singlet state and 3 triplet states. This is singlet states anti-symmetric, and the triplet states are symmetric, if you remember. 1 minus 1 is symmetric. So you see here, we have two anti-symmetric, right? So then, because as I apply to here, the total states be anti-symmetric, so we can only select this one, that is spin L, spin S0. So that is this one. This one does not, because this one is spin symmetric. For this case, right, S equal to 1, right, 1, 1, 1, right, is S. So that is not. I mean, it's okay, I just try to let you know how to apply. So then finally, in this case, since we have only 1, we don't need to go further. So that is this one. This is step 4, so step 4. Actually, this is a step 3, right? And this one, let's go to. We can, in this case, step 4, we don't need to apply because we already determined that is the only one possible respond to this. Okay, so that is one example. Think, remember that is for the closed shell, one example. Now let's consider the second one. Then another closed shell. In this case, how many? The atomic number? 10, yes. So, let me just, I don't need to, okay. Step 1. Step 1, so now I'm going to occupy according to the energy order here. 1s, only 2. Then we have to go to, remaining 8, go to second, right? Second s, 2s, also only 2. So we still have a 6, right? So another 6 just failed the 2p, right? Because 2p can have occupied maximum unit of 6. So here, okay, we have this determination. Then we go to step 2. In this case, I'm going to use this one because this is in the closed shell. This is a simple ether way, and this one you need to analyze. This is very complicated if you have 10 electrons, right? So now let's just save time. So now let's first try to find the total. Orbital angular momentum, so I'm going to use this way. The first shell, this one, I use the notation U1. Second, 2s subshell, and the third one, 2p subshell. So that's the first sum of each individual. Then the first L1, that is L1. The first 2 electron, right? And since this is s orbital, sorry, yeah, s orbital, so that is 0. And similarly for L2. Again, 2s, L3, L4 is again is 0, s orbital 0, 0, so that is 0. Now the third subshell is, we have the remaining 6. So L5 plus L6 plus L7, L8, L9, and L10. Now this case, we need to remember what is L. The L are 1, right? All the L is 1. So if you remember, I just drop here. This is the L, right? Li, I'm going to say, equal, correspond to the L to 1. So here, that is M, L is 1, right? And down to here, this smaller one is M, L to minus 1. And here, M, L to 0. So only have 3 possible orientation of this orbital angular momentum for each. One is here, another here, right? Only these 3. So if only these 3, you can see here. The first, if L5 go to up, ML equal to 1, so I'm going to use 1. Then the second one is 0. Third one is minus 1. We go down, right? Then this remaining 3 is same thing. So first go up, 1, 0, and minus. So you see they cancel. These vectors, I use vector because it's up and down and 0. So total. Okay, I know this is many vector operator addition, so we just use this basic idea. You know this orientation. So those orientation, since they cancel each other, so finally the total is 0. So the total L is 0, right? Total argument is 0. So that means the quantum number for those contains 0. Similarly, S is, I'm also use the shell, 3 subshells. So each one, the first subshell is up and down since it's spin only 2 electrons spin up and down. So that gets 0. Similarly, second 2s is also 1 up, another down. So that gives us 0. The third, we have a 6. So according to Pauli exclusion principle, if a 3 up, then another 3 is spin down. So all cancel. Again, give us 0. So we have total S is 0. That gave a quantum number is 0. Any questions? Okay, so now once we have a total number L and S, then J is between this, right? Because it's total, this is orbital and spin counting. Total orbital plus total spin. So here this is 0. This is also 0, so G is 0. And then the go to S is 0, so the 1, L is 0, is S, J is 0. That is the ground state spectrum, scopic notation of neons at ground states. And okay. Here, yes?
I understand how you got S, but yeah. How did you get L? Like, how did you determine that L5 is 1, L6 is 0, L7 is minus 1?
Okay. So there are only 3 choices, right?
Right.
So if I select this one as up, you must have another down. Mm-hmm. And then another. So there are 3 choices, right, for these 3. and then another 3. Because the reason why these two can the same direction because spin up and down, so we have a lot. There are two the same, another two because it's fully occupied. So all the possible direction or use, right? Then cancel each other because it's a closed shell. So that's why we got this. So now the conclusion. From here, this from these two examples, we can extend to the original for all closed shell, whatever the number of electrons, the spectrum equation is always this one. Because we can see for closed shell, all the occupied, fully occupied, spin cancelled, and occupied moments also cancelled. So L speed 0, S speed 0, then the J also 0. That is for all this closed shell. That is easier. The difficulty is for this open. So now let's play this open. See how they play by those strategies. Can I erase this part for the feeling? Okay. Now, this B is open. In that case, it becomes the first one. Let's consider the boron. Boron Z is 5, right? So the step 1. Electronic configuration here. So we have 1s be 2 electron, 2s, another 2, and then the remaining ones we go to 2p1. So in this case, because only 1 electron, so you can either up, down, or 0. So all the possible is here because no any other. Right, so here. Okay. Then step 2. Step 2 here, let's consider the total L first. L is L1 plus L2 plus L3. And as you know, L1 is 0. Same thing like L1 is 1s, right? So for s orbital is 0. 0 plus 0 is 0. And the second shell for the 2s also 0, since 0 plus 0 is 0. So we have 2 electrons in the 2s, 0 plus 0. 1s 0. Now the only one is L3 is okay, in this case, I'm going to use L5. L5, as I said, any direction is allowed because it's open, right? So I just use this one. So from here, you can see the total angular momentum only defined by the, only the subshell is not fully occupied. So all the occupied you can ignore, right? So that means later, you just consider how many electrons occupy the open shell. All the fully closed shell, that contribution 0. So we just consider this, right? So here, from here, immediately got this L speed equal to 1 because only 1 L and lower L is 1, right? So it's a P. S. Similar thing. So that is first one S. 1s shell is up and down, cancel. 2s shell is subshell is also up and down, cancel. And 3 is just S5, only 1, right? So that is also only depend on the electron come from the open shell, open subshell, right? So then here S is half, right? So the S, the magnitude is half, and whatever the spin up and down, that is half. So we immediately got this. Then now J. Another J value for giving L and S. So that gives us J equal to, when L equal to 1, S equal to half, so that is 3 half, right? So this is 3 half, and L minus S is half. So we have J has a 3 half. Okay, let's just use small one first. Half from lowest case, from the small one, 3 half. 2 values. This one, okay, that's enough. Two values. So the spectrum scopic notation 2s plus 1 L here, that gives us S is half. 2 multiplied half is 1. 1 plus 1 is 2, right? So this is 2. L is 1, so that's P of 4, right? L here. Then J here, we have 2 values. So we have 2 spectroscopic notation. That is come to here. And then we are going to see which one is the lowest we are going to apply. Here, since this is only this, these two, and the L and S, okay, now, this is for to determine L and S. So step 3 is we are going to apply, since you know the wave function is the product radial part and total angular opto and total spin. So that symmetric antisymmetry is to determine these two numbers. For J, we always apply the Holmes rule for this, the third Holmes rule here. When L and S determine, so it is calculated. So J will apply this. Therefore, the step 3, sometimes we need it is if we have several L and S, then we are going to use the symmetry to help us to filter out which has wrong symmetry. Then the remaining part we are going to apply this Holmes rule. But in this case, L and S is fixed. So now, the only for this, we just go to jump step 3, we don't need it. Come to the step 4. Okay, step 4. It says, here S and L already fixed, right? So only this one. Because we have 2 J's, so which one is L minus S or L plus S? It says, if this open shell is filled less or equal to half subshell, L minus S is J. It's more than the L plus S is J. Now we have only one, less than half, right? So let's go to this one, L minus S. Is 1 minus half is half. So that means the ground state spectral notation is this one.
So how do you know which shell to put in there, like S or P? Like for neon, we chose S, obviously. Over here we use,
You mean occupation, right?
like in the spectroscopic notation itself, like in our final answer.
Yeah, this one, right?
Yeah.
Okay, this one since we know here, I think I didn't, this one already gave L is 0, right?
Mm-hmm.
So here's S. Okay, here, S is also 0, right?
Right.
So L0, S0, then here, S0, that is 1, fixed.
Right.
L0 is S, so not only J. And since L, J here, because LS is 0, L minus is the J only has 1 value, is 0.
Okay.
That is determinism. Okay, now come to this one. Again, so the more difficulty is L and S, because that is summation for all the electron orbital and its spin. J is when L and S fixed. We just follow this. So for LS, this case simple because for boron, the open shell only 1 electron. So L and S, and S is given, right? Fixed for single. Then when LS fixed, we can use this relation to determine how many J's. Then apply the Holmes rule, the last one, the third one, to determine which one. Among these two, which one is L minus S, this one. Okay. Now, if we go to carbon, you will see, if you complicate it, since we have 2 electrons in the open shell, so we need, you will see this, we will apply all these 4 steps to carbon. Atomic number 6, right? So first step 1, the configuration 1s, 2 electron, 2s, 2 electron, and 2p, sorry, 2 electron, right? So that is open shell. Okay, so then we go to the step 2. Step 2, it is, let's just quickly do this one. So, okay. Step 2, let's first consider this, the two, okay, so the total orbital angular momentum is, again, we have first subshell, second subshell, and third subshell. So 0, the first one is S orbital, S orbital, the second one. The last one is, we have 2 P orbitals, right? Sorry, this is 5, 6. Right? These two. So these two, remember we have 3 choices, ML up, down, and 0. So we do not know how much is it depend on this up. ML into 1, ML into -1, and here this ML 0, right? So with this case, this two may be all the up, maybe one up, maybe one down, maybe one up, 1 0. We are going to cut, so there are several combinations of these two orbitals. Then we are going to select which one is ground, right? So this is a little bit complicated. Now here, I'm going to keep here, that is, you can see again, that is controlled by this outer and open shell electrons. So all the closed shell will reject and ignore. Same thing for the spin. Spin first subshell, second subshell, third subshell. Again, that is 0 because they fully occupied up and down. So either up and down according to the Pauli distribution principle. The third subshell will have S5 plus S6. This one also, maybe they are same, they are one up and down or one down because this a lot. There's 6 states can be like this 2 electrons occupied, right? So now, in this case, first again you can see this is also controlled by this electron outer shell. Okay, so now, how much? Then we are going to apply the addition of angular momentum, which we learned in chapter 5. Okay, so here, since L1, L5 and L6, the quantum number is 1, right? Because the p orbital. Okay, so now S5 and S6 all are spin this part. So now we know this number. Then addition, so now we are going to apply the addition of angular momentum. Here for L, let's count L be smaller or equal to L5 plus L6, right? Larger or equal to the difference between these two. Then here, this is 2, right? 1 plus. This is 0. So that means L, there are 3 values. And these 3 values is dependent on these 2, either both are up and down or cancel, right? Okay, so S. For S, again, S is smaller or equal to S5 plus S6, larger or equal to the difference S5 minus S6. And this is 0, this is 1. So that gives us S is 0 and 1. Now we have, for giving S, we have different L, then we have a different spectrum notation. How many? So now we're going to see G value, right? G is now we are going to determine G is so that has a possible value depend on S. So now let's select S equal to 0 and L equal to okay, so if x equal to 0, L equal to 0, so only 0, right? And if s equal to 0, L equal to 1, then this is 1. S equal to 0, L equal to 2 is 2, right? So this spectrum, this one corresponds to this one corresponds to S, because L is 0, right? S and this 0 is 1, G. Right? So this one, S 0, L 0, and G 0, so that is this one. From here, right? This one, S still 0, but L is 1, G is 1. Okay. This one, S 0, but L is 2, so D, G is 2. So we have these 3, right? This is for S equal to 0. Now, let's consider S equal to 1. And L from 0. L has 3 values, right? Then this case, so S equal to 1, so that is 1, right? Because L equal to 0. And S equal to 1, L equal to 1. And here is a 2. So we have a 0, 1, 2. 3 possible values. A J, right? Because this S equal to 1, L to 1 is 2, and this minus 0. So J from 0 to 2. So we have 3 values. Then another one, S equal to 1, L to 2. Here, 2 minus 1 is 1, right? And then this is 1. I think that's a bit more. 3. 1. So that is a 3, 2, 1, right? 2 minus 1 is 1. So that is the 3 value for J. Now the spectrum of here, right? So this one is S equal to 1 is 3, L equal to 0, so J equal to 1. But here we have S3, right? S is 1, so 3, right? L is so P and 0, so we have 3. Then the remaining one is again 3, but D, L is 2, right? 1, 2, 3, 2. So now how many? Many, right? 1, 2, 3, 4, 7, 10. So now the question, among these 10, which one is ground state? Then we are going to apply. In this case, we need step 3 here. Since now we have several S value and an L value, we are going to fill out some S and L such that the wave function does not follow this anticipation. Then we are going to apply the Holmes rule. The reason why we need this, we cannot immediately go to here because this one does not consider the symmetry. So if you jump to here, you will get it wrong, something wrong. So we first go to here. Step 3. Okay. This is an antisymmetry. This. Okay. Antisymmetric, so there are several choices. Remember I have since we only consider the 2 outer shields, so let's go to R5. Radial part. Radial part is 2 electron. If a symmetric, then the orbital symmetric, so the spin speed antisymmetric, right? Or the radial part still symmetric, but the orbital is antisymmetric, then spin speed symmetric, right? Symmetric, symmetric, antisymmetric. Okay, or the radial part is antisymmetric, orbital part also antisymmetric, symmetric, and the spin also symmetric. The last one, the orbital still antisymmetric, but orbital is antisymmetric also, so spin speed symmetric. Spin speed antisymmetric. So we are going to use to analyze among those are those satisfied? Okay, so because for R5, R6, anti-symmetric, you will see this is 0. So because this is a 5 O are n equal 2, L equal 1, right? So they R index and L, remember for each single R5, R21, R6, and R21, R5, R21, R6 equal to 0. And that makes sense because these 2 electrons all are in the same subshell, all are 2s. Sorry, 2p, right? So this energy level the same, then therefore is no, according to, this antisymmetric oscillator is 0. So R, the real part, only non-zero is symmetric. So if symmetric, that means these 2 does not exist, right? If we have the radial part antisymmetric, so we go to here. Go to here, now we are going to see the orbital wave function either symmetric or antisymmetric. Sorry. Spin, same thing. So now we are going to consider the orbital and spin. Here, since it's a simple case, this addition 2 electron, 2 orbitals, right? So we can use the addition. Now we are going to see for L. L here. Which one are symmetric? Which one? We are going to find correspond to symmetric, which values? Correspond to antisymmetric, which values, right? We are going to see this. So, sorry, this for L. Okay, let's consider for L. We are going to addition, apply addition of momentum again here. Since these are 2 orbitals, so here L and L. How many states? L equal to 0, M L equal to 0, right? Because L has a 0, 1, 2. So when L equal to 0, M L only 0, right? Because M L is plus, minus L and minus and 0. So now that is states. Second one is 1, L equal to 1. So we have how many states? 1, 1, 0, 1, minus 1, right? So that is for L equal to 1. M L is plus, minus 1 and 0. 3 states. Then the next one is L to 2. So we have 2, 2, 2, 1, 2, 0, 2, minus 1, 2, minus 2. This is for L to 2, and ML is plus, minus 2, plus, minus 1, 0. So totally we have 9 states. Now we will ask ourselves, among these 9 states, are they symmetric or antisymmetric? We are going to separate, and then we are going to see if antisymmetric, we have to go to the spin symmetric. If orbital symmetric, spin antisymmetric. Others are not exist, right? So I just want to save down. Each one we can use this later. Golden coefficient. So that's you just take table. If you have a table with your hand, you can find for which one, for 1 by 1, because two orbital L5 is 1, L6 is 1, right? So just remind you, you have the table if you want to. This one. So 1 by 1 is here. Yeah, this one. So you can check yourself. I just want to save time. from this table we will find out the antisymmetric, this is antisymmetric, sorry, symmetric. This one is symmetric, and those are symmetric. Well, L equal to 0 and L equal to 2 are symmetric. These are symmetric, and L equal to 1 are antisymmetric. Okay, once we know this similar thing for S, ms, the total spin, then we have how much, since S, we have 0 and 1, and we already know that we have a 4 state, 0, 0, for S equal to 0, ms is 0, and this is 1, 1, 1, 0, 1 minus 1 is for S equal to 1, ms equal to plus minus 1, 0. So among the 4 states, again, you found this, take the table so you can see here, 0, 0 is antisymmetric, 1, 1, then S equal to 1 is symmetric. Triplet, remember now. Okay. Now, once we know this, so we can come back to here to fill out those which one is about, right? So now, since let's look this one. There are only these 2 possible, right? One is if orbital symmetric, spin antisymmetric. So for the possible for this case, now we select L. For L here, symmetric is L. So for this one, L should be 0 and 2, right? L, either L to 1, 0 and 2, those are symmetric. And for the S, antisymmetric is only 0. Okay. So that means then this G, okay, I think that's probably enough. Let's just do this. So here, that is for this case. For S equal to 0, we have 3 types, but now L only L equal to 0 and 2, so this one not exist. So that means the possible is S1, 0, and 1D2, right? So 1P, 1 not. Does not exist. That is we analyze this step 3 to drop this one. Similarly, L is antisymmetric, spin is symmetric. Then we have L is equal to 1, right? Out here. These 3 states correspond to L to 1. And then the spin symmetric is S equal to 1, right? So that is correspond to this case. Now is here. S equal to 1, L equal to 1, only this one. This one not exist, right? L equal to 0 and L equal to 2 will not exist. So in this case, only P 3P, then G, we have a possible 0, 1, 2, right? 0, 1, 2. The others, okay, this not exist, those not exist. So that means all the D, 3, 1, 2, 3, not exist. Now we are going to apply Holmes rule to take which one is lowest, right? After step 3, so we have now we have this and this. Now apply. The first one, S, go to maximum value, right? So which one, S max? This S equal to what? This S equal to 0, so it must be here, not here, right? That makes sense? According to this. S is select the largest one. So we have allowed this group and this group. Among those, this group one. This is S equal to 0 case. This is S equal to 1, so that will come to here. So that means S is take 1. Then the L is the largest. Actually, in this case, since S already limited here, so there's, even though this L is bigger, but since S does not satisfy, we just come down here. Right, so filter those, since here is S maximum. Then among this, L only one value, right? So L is, in this case, L is 1, because P. Then now, number 3. If the less half shell, so in this case, yes, because half is 3 electron, we have 2. So we are going to apply L minus S. So GS equal to L minus S, L maximum value in this case, minus value, which is 1 minus 1 is 0. Is this one. Right? Among these 3 is GS 0, 1, 2, so this one. So this finally, this is the ground state. Spectroscopic notation for the ground state of carbon. Okay, this is complicated. Now, let me see. I'm going to give you, since I think we still have a little time, give you an easier way to skip. I will introduce an easier way to skip step 2 and 3. And that means we are going to give you an easy way to try to find the S and L, and what we need to just apply this. Once we have the electron configuration, so you just use the easy way, which I developed, and then apply this. When I say I developed this when I was an undergrad student, and me and my classmate, we saw this interesting and tried to see if I can figure out a formula to determine L and S. And of course, this is published in Chinese, so sorry. But that is when almost after the graduate from the undergraduate with bachelor degree, then we spend the time try to figure out the law and it's a simple way, and later you will double check. Very easy. So now, actually, I recently checked the website and found some others also found or summarized or developed the formula which similar with us, but that is after our publication. So here, the goal is try to determine L and S, right? After, so now let's find the first electron configuration, right? Electron configuration. Once we have this, now the second one, for S, we immediately go to the S. S equal to sum over, now let me give you the formula. And you will double check yourself and select any arbitrary element from periodic table. Once you know this configuration, you just apply this method, you can really get this spectroscopic notation for ground state. So S is half of N 1 minus N2 plus half of P1 minus P2. So this one is the first subshell. This one, if we have several subshell which are open. Second, if we have more, right? So that is N1, P1 is the number of electron occupied on the first half. The first half of this subshell. And the N2, P2 is number of electron second half of the corresponding subshell. So when we discuss, these are all numbers for open. For closed, of open subshell. Closed, as we already discussed, it fully occupied, so there's no contribution. So example here, if we have a calculation is the 4S1 and 3D7. Before that is all are fully occupied. So if this open subshell is this, so now S equal to here. So half of what is N1? 1, right? Because we have 1 in the first half shell since there were 2. So 1. But second half shell no electron, right? So that is 0. N1 is 1, N2 is 0. Then plus second half P1, 3D. The fully occupied is 10 electron, right? Half is 5. So that is more than half. So the first half will be 5, already occupied, right? And the remaining 2 is on the second half. That is 2. So how many? Half. This is 3, right? So that is 2. Very easily can obtain this, the final, we try to figure out which X, right? So now this is the S for this. Of course, this is all for the ground state, right? Now, that is for S. For L, similarly, but L has, since S, the reason why I have minus here is because spin up, spin down. So that is used. That is according to the Honda's first law. All spin go to maximum. That means as possible as we can to occupy the same direction. Then fully occupied first half shell, you have to go down, right? So that is the minus side come from. Similar like this. Now L is absolute value of summation first half shell N1 MLI plus summation for second half shell N2 LI. If we have this is the first subshell first half, second half. If we have another subshell which is summation I from 1 to P1 MLI plus summation I from 1 to P2 MLI and O. So that is the first half, second half. This is the first half of another subshell. This is the second half of another subshell. Let's do example. See how can we determine L. Okay. Let's consider we have 4 electrons in 2p. So we know P half, first half is 3, right? So that is the first, in this case, N1 is 3, N2 is 1, right? Actually, we don't need, yeah, that is the summation. But here, what you can do is now L is, so ML, since this is I is 1, right? So ML I is plus minus 1 and 0, 3 values. So now here, for this one, minus 1 plus 0 plus 1, right? First 3 is I from all the possible L value. So that is first half. Second half is come to here. Second half only we start from, okay, here. Let me say this, the summation start from lowest, m L I from minus L and to minus L plus 1. Go to this way. So now here, this is 0, this is 1. Immediately got L. Then, once we have L and S, so J follow this Honda's third Honda's L minus S, L minus S, and L plus S, more. Okay. You see, now with this, so the only important issue is write down the correct electron configurations. Then we can immediately got this. So now let's play some examples. Let's first we'll play carbon since we already have a carbon, right? So now it's examples. First one, carbon. 6. So we know the electronic configuration is 1s squared, 2s, 2p. Sorry, 2. Okay, once this is correct, now let's try to determine s. Only open shell we have 2, right? So s is a half of 2 minus 0. Since the first half, we can have up to 3 electrons. So we have 2, and the second half 0. So that is 1. Very quick, right? And L is a summation I from 1 to here. Okay. Even though here is, since we have only 2, right? And L I. So that is from minus, right? From minus 1 plus 0. So the summation from lowest to highest. Now we have 2 electrons, the orbital MLI from minus 1 and go to 0, go to plus, but now we have only 2. So this is 1. And then J, okay. So since J here, S equal to, so now J equal to L minus S because this is a less than half, right? Here, right? This one. So 1 by 1, and 1 minus 1, 0. And that is S3. This is S1, right? So that is 3. L1 is P. Remember we got this one, spent a lot of time, but now if you use the very easy method, you can quickly get it. Let's do one more. So second one. Because this one textbook paper, this one. Let's just go to the one which textbook is paper. So I want to correct that one, which is Cooper. Chronic, not Cooper. For this case, the atomic number is 24. So the configuration is after the argon. Argon is fully occupied, right? And remaining, we have a remaining 6 electrons. 4s, okay, here, that's B1, not 2. And then go to 3d5. So here, textbooks make mistake is, this is wrong. The reason wrong is there's another issue. Of course, this is deal with the spin coupling or spin orbital coupling. When the d orbital, if the 4 is, there's only 1 go to the fully half, right? So in this case, all the spin are fully occupied. This energy is lower than this one. So instead of to occupy like this, first occupy the 4s fully occupied, then go to the 3d. But 3d has only 4 spin up. But if we have a 5 spin up and 1 goes, so this energy is lower than this one. So that is the correct one. Okay, this is in textbook. I think page for, you can see the table page. $472. That table. So now we are going to use this. Okay, with this correct one, now we can easily get S. So we have two subshell open, right? That's the first one is 1 minus 0, because only 1. So M1, number of electrons occupied the first half is 1, but the number of electrons occupied the second half is 0. Now second subshell is 3D, right? Half of 1p. Sorry, p1. p1 is the first number, so that is 5. We have 5. But second half is 0. So totally half, so that is 3. Yes, it's 3, right? Okay, then L, that's, we have several subsets. So now 5 from 1. And this N1, that's N L5 plus I from 1, sorry, yeah. N2, N L5, and we have two subshells, so 4 half subshells. 1 to P1, N L5 plus I from 1 to P2. Then now first one is only 1s, right? So that is 0. Right? First, L is x. Is 0, right? So that's 0. L is 0. So no, and this one is also 0 because no electron occupied the second one, right? Now go to this d orbital. D, first one we have 5. So from minus 2, minus 1 plus 0 plus 1 plus 2. Since they fully occupied, all star up and down cancel, and that is 0. And the second one, no, that's 0, so that is 0. Okay, then now let's select G. G, in this case, so it is L is 0, S, okay, yeah. It's L minus S because this one is equal half, right? So still half, so that is still apply this one, not this one. So that is 0 minus 3 is 3. Okay, now the ground states, the spectroscopic notation is, S is 3, right? Yeah, 3, 2, 3, so 7. L 0, S, and G, yeah, G is 3, yes. And this one, correct in textbook. So they just made a mistake on this conversion, but the spectral notation they made it correct.
Why is that electron configuration?
This was like this, as I said that if the d orbital, so now this configuration has 4 up, right? But it found that this is also very commonly due to this coupling interaction, so that we found this one energy is lower than this one. So that means if I have 6 electrons, I prefer the first 5 to go to here, and the remaining go to this. So that is lower than this one, energetically. And you can find from the, you got the internet to ask us what is the electron configuration of chromium, and there's one discuss this. Okay, so you can, with this method, we double check in our paper all the elements in periodic table up to 101, in that 07 in that time. That is several long time ago. But now we have some new element. You can use this method to determine the spectroscopic notation for new element, or you can predict. Okay, good. So we finished the chapter 8. Then from next Monday, we are going to discuss the perturbation theory. Consider if the potential is very complicated, we cannot get its exact analytical solution. How to do that? Then one example we can go to your like hybridization, how to determine the bond. If you have two atoms with a hydrogen molecule, or helium with a helium light with two. I think that one is two hydrogen molecule is two molecule for two atoms, and another is a helium with a ionic light. So that one is fine. I think I need to remember another one. Okay. All right.
So whenever you're counting in this sum, do you always start from the negative value?
Yes, from the lowest to go higher.
And then go to
Follow
the
that order. Otherwise, it will not give you. Yeah, just follow that. That is the formula. Of course, this is all for ground state, right? For the excited states, we will not follow that. There is a lot of possible, no any restriction from the energy reflex lowest. Yeah.
The good news is we're almost ready to apply to your undergrad now.
I just think that one may be help in case if you do experiment, maybe sometimes you need those spectroscopic notation. Very easily you can use that. Very easily to do. Okay. Homework, which I give you two, right? The second one is give you some more spectrum. I don't remember some of like this. Or suppose I just say that suppose something like this, and ask you to guess what is. I think I ask you to find what is. Ask you to find G, right?
Yeah.
Remember, yeah. So you know how to do it, right? Yeah. You have S from here. You can find S and L, then you can find G.
Yeah.
The first one is takes time. You have three particles, but ignore spin, so that makes since it's a bit easier. But since it's three, there are a lot of computation for ground state. The first exercise is consider all the possible.
I think that homework question 2 is pretty straightforward, right? You just take that and then
Yeah.
set it equal to like 2s plus 1.
Yeah. That's what S is. This is 0, and L is yes.
Okay.
Yeah.
That makes sense.
Just to let you familiar with this spectroscopic notation. All right. Thank you. I'm going to post the solution of the midterm exam on Blackboard, so you can check and see where to help you to understand your mistake. If you still have questions, let me know. Okay.
I actually have a question
Yeah.
on that, because,
I make more, yeah.
yeah, so
Yes.
if n is equal to 3,
Yes.
L's only n minus 1, right? So why would we do the L equal 3?
No, L, okay, that is another concept. L equal to n minus 1 is for hydrogen atom. This is the isotopic harmonic. There's no such restriction.
You saved me,
Go back to, if,
Okay.
I think, go back to the textbook or to my notes. When we derive, you will see there's no such restriction on it.
Okay,
Yeah, yes.
that's why I didn't do the L equal 3, 'cause
Yeah,
I just immediately.
I know some of you, not only you, the others also, think about n minus 1 is L maximum value of L.
Okay.
But that is for hydrogen.